Yeah. Yeah, register and download the data. And save all the 3 files in a folder. So while we are importing data pre-processing, this is the most critical or important step in data science. Your 95% of time spent on data pre-processing. On this task. And the success or the failure of the project also will depend on how you process the data. The success and the failure of the project will also depend on how you process the data. So data pre-processing is the most critical and complicated task within the data science. Now, it's a very, very wide area. It's a very, very wide area wherein each data presents its own challenges. Each data has its own challenges. Multivariate data has its own challenges. Time series data will have its own challenges. IoT data will have its own challenges. Medical data will have its own. So we can't say that pre-processing is same for all the data. It depends on data to data, and how we are going to deal with it also is complex task. Keeping in sense that we are focusing on machine learning and we are going to work on multivariate data, the following data pre-processing steps are critical because we are focusing more on machine learning, and machine learning is done mostly on multivariate data. Multivariate data means you'll have a lot of independent variables that will be both numerical and categorical. And you might have a numeric dependent variable or a non-numeric dependent variable. So there we do multivariate data analysis. Now, the pre-processing task which I'm going to talk will be more towards the multivariate data. As we go through different data, different pre-processings, I will explain to you according to that data. The first step in data pre-processing is check for duplicate columns. We have to check for duplicate columns. This is one of the first tasks we ask to do. Whenever you get data, you always see whether there are duplicate columns. So either through visual inspection you can do. You can just print the columns and then see the data, or a detailed data dictionary. Wherein each variable is explained in detail must be created. whatever variable you have in your data, there must be an explanation of that variable. Now, if you see the problem statement here, see each and every variable is explained. This we call it as data dictionary. This we call it as data dictionary. Each and every variable will be described. In industry, we'll add another column wherein we also add data type, whether it is an integer, float, or object. Data type will also be there. Then we will also add another column, whether it has missing values or not, that also we can do. So data dictionary, this is the basic format. Based on your working and based on the data you are dealing with, you might add some more columns to the data dictionary. So one of the common column is data type. D type will add to the data so that we can understand what type of data we are dealing with. So this is an example of a data dictionary. This will help you to rule out any duplicate variables. Sometimes duplicate variables have differential names also. Right, we have seen duplicate variables with differential names. So then we have to be very careful with those variables. One of the duplicate variables which we see here is zip code and pin code. In India, because we implement the American software, zip code will also be there, pin code will also be there. People write zip code, the same pin code. In pin code category also, they will give you the same pin code. So this is what happens when your database is not properly designed, or when you are defining your database, you should replace the zip code with pin code so that you can have only one. So duplications happen. Duplications of data will happen. It is our job to eliminate those duplicate columns. Okay, so that is the first task. The second task is single value columns, wherein the whole column will have only one value. Like all will be 0 or 1. Typically, we see the whole column will have one single value. How will you identify? When min is equal to max, is equal to mean, is equal to median, you can say it is a single value column. All the descriptive statistics you get, no? They are all single value. Q1. If all of them are same, then you can say it is a single value column. You have to remove them. Single value columns must be deleted. You have to delete single value columns. Pardon? Yeah, describe for numerical. See, for numerical data, you have to do describe. For non-numeric data, you have to do value counts. You have to do value counts. For all the variables, you have to do value counts so that sometimes zeros and ones come like that only, right? If it is zeros and ones, it comes under describe only. Describe data only. Very rarely it comes under character data. That's why we are looking at describe here, because it will be 0 ones means it will be numeric only. If it is a text repetition, then we have to do value counts. Like what happens is employee over 18. All employees will be over 18, right? Yes will be there. So we will delete it. All the employees will be greater than age of 18 only. So the whole column will be yes only. There we have to do value counts. The next important and the most critical task is the missing value treatment. This is the biggest headache task we have in data science, which is the missing value treatment or dealing with NA. Because by default, empty cells will be given NA. So this is the problem, missing values. Now, if a variable has greater than 70% missing values, impute with word missing or not available. If there is more than 70% of the data missing in that particular column, we should not try to impute it. We should impute with the word called missing. We'll keep it as missing only. We'll keep it as missing only. We'll create a new category called missing, or we will input the missing values with the not available thing. If a variable has less than 70% missing values, impute with mean or median if it is a numeric variable, or mode or most frequent if it is non-numeric categorical variable. So if you have less than 70% of missing values, you can impute it with mean or median. How you decide? If mean is distorted, use median. If mean and median are both closer to one another, you can choose any one of them, preferably mean. But if there is a too much of the distance between mean and mean is distorted, use median as the imputation. And if it is categorical, we will use mode or most frequent. Now, these are manual imputation methods. So these two are manual imputation methods. These are manual imputation method that does not consider impact of other variables on missing values. So what we discussed here are manual method of imputation. Manual method of imputation where we are looking at imputing with manual methods, mean, median, or mode. And manual method does not consider the impact of other variables or observations on the missing value. It does not consider, because we will take the single column mean. No? We are ignoring all other variables. We are just taking that particular column's mean, median, or mode, and then we are imputing. We are ignoring other columns or other variables. Now, this is where the algorithm-based imputations will come into picture. Algorithm-based imputation methods consider the impact of other variables on missing value and accordingly impute, and accordingly will impute. Algorithm-based imputations. We have algorithms which are being developed for missing value imputations. This is one of the important research areas even today in machine learning and data science, and even in statistics, how to do missing value imputation such that our errors will be less. Within this, one of the most popular is missing imputation using chained equations, also called as mice algorithm. Missing imputation using chained equations. So this is a very powerful algorithm which simultaneously imputes both numeric and non-numeric variables. Missing imputation using chained equations, also called as Mice algorithm. Now, what Mice algorithm will do is the variable that has the missing values. The variable that has the missing values, if it is a numerical variable, first it will impute the missing values with mean. First, it will impute the missing values with mean. Then it will make that variable as dependent variable, and it will take all other variables as independent variables and conducts multiple linear regression and runs the multiple linear regression algorithm. As part of multiple linear regression, we will get the predicted values. Now, once the predicted values are generated, it will take the predicted value and replace it with the imputed mean value. Wherever initially it imputed mean into the missing value cell, right? Now, once it runs the multiple linear regression, it will get the predicted values and it will replace the imputed mean value with the predicted value. That is the process of mean. That's why we call it as chained equations. It repeats this process with variables that have missing values. Suppose the variable that has a missing value is non-numeric variable and it is binary variable, yes or no. It will first impute the missing value with the most frequent. Then it will make that missing variable as dependent variable and conducts binary logistic regression. As part of binary logistic regression, we will get predicted classes. Then it will replace the predicted class with the imputed most frequent cell class, and then it will replace the value and it will give you the final imputed value. So this is the process it will do. Chained equations. Chained equations means each variable that has dependent variables will be imputed initially with a value, and then according to the type, either the regression or classification will be conducted, and then the predictions will be generated, and the prediction values will be the replacement values. In this case, we are taking the impact of other variables on this missing data, and then we are imputing. Okay, so that is one. The second is KNN or K nearest neighbors. K nearest neighbors, very popular algorithm, KNN algorithm. It is also used in imputation, but KNN works only on numeric data only, as it uses distance measures like Euclidean. The problem with KNN imputer is it imputes only numeric data. Because if you have numeric data, then only you can calculate the Euclidean distance. Okay. So K nearest neighbors algorithm is also there in Python. KNN imputer is there. We can use that for imputing missing values. Then we have algorithm called probabilistic principal component analysis. This is another algorithm that is being used for imputation of missing values. Similarly, algorithms like random forest, gradient boosting machines, neural networks are also used for missing value imputation. So any doubts in missing values? So missing values, we will implement all these things. So what happens is, as of now, mice is not full-fledged in Python. Mice is implemented is in an experimental phase. We call it as iterative imputer. But in R, we have mice algorithm available. But in Python, as of now, it is an experimental stage. It will be implemented in the next version. KNN imputer is there in Python. We can use that one. And rest of the algorithms for imputation are more available in R than in Python. Okay. KNN is there, which is the one, and then you can use the manual methods. And iterative imputer is an experimental stage, which will be applied, which will be coming in the next version. After missing value treatment, the next important task is data transformation. Data transformation or transforming the data. This is also a very critical step in data science, data transformation. Now, when you are looking at dependent variable, data transformation of dependent variable, if the dependent variable y, let us say the dependent variable is often noted as y, has positive skewness, then we will do logarithmic transformation or square root transformation. Similarly, if there is negative skewness, we use opposite of logarithm, which is exponential transformation or the power transformation. Exponential transformation or power transformation. This is for dependent variable. And if none of the transformations work, then algorithms that are resistant to skewness and outliers like decision tree, random forest, gradient boosting, or the KNN must be used. If you are not able to deal with skewness and outliers by transformation, we have to go to the next set of algorithms. Your basic algorithms like multiple linear regression or logistic regression will not work. They will not work. If they are not working, then we have to go for the advanced algorithms like decision tree, basically tree-based models. Tree-based models are not sensitive to skewness and outliers. They will give you proper output even if there is skewness and outliers. This is the data transformation on dependent variable, y. The variable which you are analyzing or the variable that you are predicting. the variable which you are predicting. The variable, you have only one variable which you have to predict, or you have only one variable that will be your target variable or predicted variable. That variable we call it as dependent variable, denoted by small y. Now this dependent variable will generally be given by the client, or if it is not described, you have to come up with the right dependent variable. So in the problem statement, it is clearly given here. See here, the sales of the product to the particular store, this is the outcome variable to be predicted. And you will not see the dependent variable in test data, because you have to use the training model to predict on the test data. So in test data, you have all other variables except the dependent variable. See, because using the model that you are building on this data, we have to predict on this data. Then we will get the predicted item outlet sales. Then we will submit it into the competition. So there will be a variable which is called as small y or dependent variable. No. This is completely different. Every data will have a variable which will be the most important variable, or we call it as the predicted variable or target variable. In statistics, the word used is dependent variable. It's denoted by small y's. It will be only single variable. It will only be single variable. Then comes your independent variables. X's. There will be multiple independent variables, X's. Now, numeric independent variables. Numeric independent variables will be there, and then we also have non-numeric independent variables. But we will be working, transformation is applied only on numeric variables only. Okay. Now, the first one is standardization or standard scalar or z-score, which is x minus mean divided by standard deviation. You will replace the values with z-score. You will calculate z-score of each observation, and you replace it with that values. Standard scalar is mostly applied on multivariate data, and it tends to bring data closer to normal distribution. It tends to bring data closer to normal distribution. Standard scalar scales data into both positive and negative values within a range. Standard scalar or z-score is generally applied on multivariate data, which brings data closer to normal distribution, and it gives you both positive as well as negative values within a particular range, +5, -5, +3, -3, depending upon the variables, the values you have. The second is normalization, or also called as min-max scalar The formula is x minus x min divided by x max minus x min. The second type of scalar is min-max scalar. Min-max scalar will scale all data into the range of 0 to 1 without any negative values. Whatever may be the values you have, it will scale the data between 0 to 1. And no negative values will be generated. Mostly used in image processing and large-scale data analysis. So, the normalization or min-max scalar, x minus x min divided by x max minus x min, will scale the data into the range of 0 to 1. 0 to 1 only. And no negative values, only positive values. The third type of scalar is robust scalar. Robust scalar, the formula is x minus x q2, x minus q2 divided by q3 minus q1. X minus second quartile divided by q3 minus q1. This scalar is best suited when there are too many outliers and outliers are affecting the model performance. Then we will use robust scalar. Robust scalar will be used when you have many outliers in your data. When you have many outliers in your data, you have to use robust scalar. Formula is x minus median or q2 divided by q3 minus q1. And one important thing is, do not scale label encoded or dummy encoded variables. Dummy encoded variables, dummy encoding is process of assigning numeric identifier to classes or levels in categorical variables. So what happens is, there should not be any text in our data. There should not be any text in our data before we send the data to algorithm. That means all the text values must be assigned a numerical identifier. Take for example, we have a column called gender, male and female. So we have to dummy encode them. Dummy encoding are typically done on alphabetical order. Female comes first, so we will assign 0. F comes alphabetically first. So female will be assigned a value called 0. Male will be given a value as 1. So 0 and 1 will be replaced with male and female. This we call it as dummy variable encoding. Some variables you have yes or no. Yes or no also same thing. Alphabetical order, no is assigned 0, yes is assigned 1. So when you have such columns, you should not include them in scaling. You should not include them in scaling. Scaling must be done only on numerical continuous data. Numerical data, pure numerical data only, you will do transformations. You should not do it on what you call dummy encoded variables. That you keep in mind, because this is one thing where people just run the scalar on whole data without segregating the numeric variables.
Sir, I have a doubt.
Yes, please go ahead.
So this categorical data, what we have, if you do some transformation, like square root transformation or something like that, and whether we can use that in that way, sir, then we can go for standardization.
No. We should not do anything on dummy encoded variables.
Okay, sir. So it should be like 1, 0 means it should be like that only.
0 and 1 only. No, you should separate them, and after separating them only, you should run the transformations.
Okay.
Okay. Now, the fifth task is dummy variable encoding. Dummy variable encoding. Assign numeric identifier to classes or levels in categorical variables. Now, there is a change here. Dependent variable y, dependent variable y in classification problems, will be either binary. Binary means yes or no, or multinomial, that means more than 2 levels, right? Dependent variable in classification data will be binary or multinomial, yes or no. Will the employee be promoted, yes or no? Will loan be approved, yes or no? Will customer default on credit card, yes or no? Like that, we have dependent variables. Dependent variables is binary or multinomial, then we have to use label encoder. Label encoder that encodes the variable within the same column, by assigning values from 0 to n levels in alphabetical order. So label encoder will do the encoding in the same column. In the same column, it will do the encoding, just replaces the text with the numbers. So take for example, our y is yes, no, no, yes, yes, no, yes, no. This is our y. Then what it will do is y underscore label encode, will assign the numerical identifier in alphabetical order. So when I say alphabetical order, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0. So it will do it in the same column. It will replace the Y with this column. That's all. It does not add a new column, nothing like that. It will simply override the existing column with numbers. So your data number, your shape of the data will not change. When I say shape of the data, number of columns will not increase. Okay. Now, for independent variables, access, we have to use something called pd.get_dummies. pd.get_dummies will create new columns based on the number of levels in variable and uses binary encoding. Binary encoding where yes is assigned 1 and no is assigned 0. So get dummies will create new columns based on the number of levels and uses binary encoding 0 and 1, yes or no. So the number of columns or variables will definitely increase. So this is very important in get dummies. Now take for example, I have a column called gender where the data is male, female, 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 male, and male. Okay. Now what it will do is it will create a new column called gender_male. It will create a new column called gender_male and it will start encoding. 1 will be assigned if the value is there. If the value is not, 0, 0, 0, 1, and 1. Similarly, it will create a new column gender_female and it will assign the opposite values 0, 1, 1, 1, 1, 0, 0. And it will delete this original column. Delete this original column and delete the original column gender. After dummy encoding, the original variable column is deleted by default. Now, if you want to retain, you have an option for that also. You have an option to retain the original, but by default, it will delete the original column. And here, it deleted one column, but it created 2 new columns. Suppose you take education. You might have 10 types of educations. Then it will create 10 types of education underscore graduation, education underscore post-graduation, education underscore high school. Like that, it will create columns and uses binary encoding 0 and 1. 0 being no, 1 being yes. This is a very important process. There should not be a single alphabet in the data before you send the data to what we call algorithms. There should not be single. If there is a single alphabet anywhere in the data, the algorithm will fail and simply say string detected. So you should not have any alphabets or special characters, nothing. All the data should be in numerical format. Then only the algorithms will run, be it in R, be it in Python, be it in SAS or any other software. Because softwares can read only numbers. They don't read text. Even in natural language processing, we convert the text into matrix of numbers. When we do NLP, we'll discuss. We have matrices, we have to convert the text, which is in the form of words, into a matrix of numbers. So we have document term matrix, term document matrix, TF-IDF vectorizer. So we have different ways in which we convert the words into a number matrix number. That we have to do. So this is your dummy variable encoding. Very, very important process. I'll show you this. This is mandatory for any data we work upon. Then the sixth one is working with dates. This is a very big challenge. Dates by default are read as object data. By default, dates are not read. It will be definitely read as object data. So we have to convert dates into date time NS format. This is the default format which is there in Python for date and time. Date time. There is no date, it is date time only. Even though it doesn't have time, it will be considered as date time only. So we have to do this date time conversion. Without converting, it will not be recognized as date. Once date is formatted, then we can extract variables like weekday, whether it is Monday, Sunday, like that, the month name, what month it is, the quarter, Q1, Q2, Q3, we can year, we can is month end, is it quarter, is month start or month end or start. You can integrate list of holidays into dates, and then you can find out whether it is a holiday or not. So dates is a very, very big challenge, both in multivariate data as well as in time series data. We have to format them. Without formatting, we cannot go ahead and we cannot work on date. Then comes your working with alphanumeric data, wherein we have to extract, in some cases, strings, extract object data, or numeric data, or we have to extract both of them separately. Alphanumeric. Alphabets and numbers are there in the variable, in the data. Now we need to extract. So take, for example, product identifiers. In product identifiers, we have alphabet as well as numeric in e-commerce and retail data. Product categories will be there. Typically, if it is a food item, it will start with FD. And then there will be one more categorization, like if it is perishable or non-perishable. If it is perishable, FDP. Then there will be a numeric code, like what type of product it is. Whether it is a vegetable, then there is a numeric code for vegetable. Within vegetable, what type of vegetable? Another numerical code will be there. So alphanumeric identifiers. Typically, HR data also, employees. Generally, the employee codes will be based on the departments they work for. So based on that, they will create codes. So we have to extract information from such data also, if it is there. Then create new variables from existing variables. We have to create new variables from existing variables. This is also very important task. Sometimes we combine variables into one variable, or we'll split variables into two variables or three variables. So creation of new variables from the existing variables. 9 would be correction of duplicate levels. Correction of duplicate levels in categorical data. Take, for example, male, M, male, M. All means same, right? All small male is there, small m is there, capital male is there, M is there, even M capital male is there. So we have to check these duplicate levels, combine them into one single level. This is also very, very critical. So broadly speaking, these are the steps. There will be many steps as we go through the data. When we are working on multiple data, we will come through with different pre-processing, and I'll explain to it. Broadly speaking, these are the data variables, which these are the data pre-processing tasks, which we generally execute on a multivariate data. Okay, so let us import the data. Import pandas as PD. Import numpy as NP. Import matplotlib dot pyplot as PLP. Percentage matplotlib inline. The standard libraries, and then import IO percentage CD. I will hackathon bitmap cells. So bitmap train is equal to pd dot read underscore CSV. Give the file name. Bitmap test is equal to pd dot read underscore CSV. Import both train and test data. Okay. Now, if you look at the data, print sigma train dot shape, print sigma test dot shape. So in train data, we have 8,523 observations with 12 variables. Test data, 5,681 observations with 11 variables. The one variable which is not there is the dependent variable. The dependent variable will not be there in test data. That is why we will have one column short. In data pre-processing, whatever is done on train data, same must be done on test data. Whatever pre-processing you are doing on train data, exact same pre-processing must be also done on the test data. We can't have differential pre-processing. It has to be same pre-processing. So it is always best to combine or concatenate both train and test. It is always best to combine both train and test for pre-processing. For pre-processing, it is always best to combine or concatenate. But for concatenation, the number of columns must be same. The number of columns must be same. Number of columns and sequence also must be same. But we don't have the equal number of columns, right? So what we do is, we will temporarily add dependent variable. We will temporarily add dependent variable to test data for concatenation. For the purpose of concatenation, we will temporarily add the dependent variable to test data. So, bigma test, square bracket, single quote, be careful with the exact, you have to give exact name. Outlet underscore sales. So this is the dependent variable. I capital item underscore O capital outlet underscore sales S capital. This is the name of the dependent variable which is there in the train data. I am giving the same variable in test data and I am filling that cells with the word test. So I am adding the column to the test data and then I am filling that column with the word test, so that we can use it as a conditional operator later to separate the data. Now we will combine the data. Combine df is equal to pd dot concat, open bracket, square bracket. First paste all the columns of bigma train, comma. Second, below it, paste all columns of bigma test, comma. Axis is equal to 0. Now, axis is equal to 0 is row-wise concatenation. That means first it will paste all the rows of train data and below it all the rows of the test data will be pasted. Axis is equal to 0 is row-wise concatenation. Axis is equal to 1 is column-wise concatenation, side by side. All columns, next to it another set of columns. Whereas axis is equal to 0 is row by row concatenation. First it will paste all the bigma train rows and below it all the bigma test rows. I am adding temporarily we have to add dependent variable. See, we have one variable short, right? That means you can't concatenate. So I am temporarily adding that variable. What is the variable that is short? The dependent variable. The dependent variable is what? Item outlet cells. So I am adding it to the test data. The name should exactly match, right? And then I have filled it with the word test. We can't leave it empty, right? We have to fill it with something. So I have filled it with the word test so that we can use it as a conditional operator later. Equal to test, not equal to test. If it is equal to test, it becomes test data. If it is not equal to test, it becomes the train data. So it's easy for us to separate also. And then we can combine df, we have concatenated. To check, combine df dot k. So we have 14,204 observations with 12 variables. Okay. Okay. Before we take a break, let's just identify missing values. Combine df dot is null is a function to identify the missing values. Dot sum to total the missing values. Dot sort underscore values ascending is equal to false. Is null is a function to identify missing values. Dot sum is to total. Sort is to sort the descending order sort. So we have missing values in outlet size. We have missing values in item weight. Is null is a function to identify NAs. Dot sum is to total those NAs. Sort is to sort it in descending order sort. Highest missing values on top in descending order. So in this data, only two variables have missing values: outlet size and item weight. Okay. There is one more method to identify missing values, which is combine df dot info. Now in info, whichever variable is less than 14,204, Info is a very interesting function. It will tell you the data structure, which is the data frame, right? Data frame structure. Then it says 14,204 entries, total 12 columns, and then each columns. Now, whichever column value is less than 14,204, that will be missing value column. So you can see here, item weight has 11,765, which indicates it's a missing value column, and outlet size 10,188, which indicates a missing value column. Where rest of all have 14,204. That means there are no missing values in that particular columns. So the beauty of this info is you will also know the data type. Item weight is float 64. That means it's a numeric. Outlet size is object. Okay. So dot info is a function where you get all the information you need, including the columns where you have missing values. Okay. So we'll take a break and I will come back. Okay. Okay. So pre break, we have gone up to info. And we found out two variables have missing values. So combined here, dot outlet size, dot value counts, drop NA is equal to false. So you can see here, the missing values are 4016. There are three categories: small, medium, and high, and missing values are 4016. Now, if we add this 4016 to median, it becomes 8000. That means we are creating a bias. A large class is being created. Similarly, if we add it to small also, it becomes a too much of a bigger bias. And we can't add it to high because high outlets will always be smaller than the other three categories. So when you can't decide what to do with these missing values, the safest strategy is to keep them as missing. Impute it with the word missing. See, since imputation cannot be done with existing levels, as it may create bias, impute with word missing. It will impute it with the word missing. So combined year dot outlet size is equal to combined year dot outlet size dot fill NA. Fill NA is a function that fills the missing values with whatever argument you are giving. So I am filling the missing values with the word missing. If I run the previous command again, now you can see the NaN has been replaced with the word missing. So now a 3-category variable has become a 4-category variable or 4-level variable. Okay, so we are filling with the word missing because we can't add it missing values with any of the existing 3 levels because it might create a bias. Too much of a larger category will be created, which is not correct. So when you are not sure, it is always let it be missing only. So what I do is I replace the empty cell with the word missing. So we don't have any missing values. If you go and run the info command and this command, you can see the missing values will go up. So there are no longer missing values. The word has been imputed called missing. In info also you can check. See, 14,204 has come back to our. Similarly, combined year dot item weight dot describe, because it's a numerical variable. So we are using describe to understand the variable. So if you see here, there is not much of a difference between mean and median. We can input with any of them. Mean is 12.79 and median is 12.60. We can use any of them, so we can input with mean. So combined here dot item weight is equal to combined here dot item weight dot fill NA combined here dot item weight dot mean dot mean. You can type it in straight line. So if I run the previous command one more time, now you can see 14204, all the empty cells have been filled with mean. Okay. So we'll go variable by variable. Let us see what each variable has. Okay. Or we can do, we can split it into numeric and categorical variables and then object variables, and we can work on that also. So the first variable is item identifier. Combine here dot item identifier dot head and see the first 6 observations of the variable. They are alphanumeric codes. And if you look at closely the first 2 letters, they might represent a category. It looks like they are representing a category. So I will create a new variable called item code. I will create a new variable called item code, which is the extraction of the first 2 alphabets of the identifier. Because I believe that the first 2 letters of the identifier are indicating a item code. So I will create a new variable. I will create a new variable called item code, extract the first 2 alphabets from item identifier, and later I will delete the item identifier. Then we will delete the item identifiers, because generally IDs we delete them. Whereas there are too many IDs will be there, your model will never converge. So IDs we generally delete. But before that, deleting IDs, can we extract some useful information? Here, I believe we can extract some information. So that's what. Let us see how many categories are there. So I'm creating a new variable called item underscore code. Data frame name, square bracket, single quote, the new variable name. It will automatically create a new column at the end of the data frame. By default is end of the data frame. Combine here dot item identifier dot apply lambda x colon x square bracket 0 colon 2. String splitting. We call it as string splitting. We are taking the first two letters of the alphabet. Lambda is an anonymous function. It's a keyword for anonymous function. Like you have DEF, right? DEF where you define a function and then do it. Lambda is similar to it, but you don't need to give a name. Here lambda and the argument. Argument is x colon x0 colon 2. X is the identifier. You are asking it to extract 0 colon 2. So combine df dot item code dot value underscore counts. So we have three categorizations. So three categorizations, FD represents food, NC represents non-consumables like soaps, detergents, and all non-consumables. DR represents drinks. So three categorizations are there. Now we will retain this variable and we will delete the item identifier. We will delete the item identifier because we have extracted the item codes and this is a better variable compared to the identifier. So IDs and identifiers, we delete them. These are categorizations, codes. So there are three product codes in the identifier, FD, NC, and DR. Exactly, we don't know how many categories are there. Value counts will tell you how many categories are there. Sometimes you get 20, 30 categories also. So the next variable is item weight, in which we have already done the missing value treatment. The next variable is item fat content. So if you see the fat content, we have duplication of levels. We need to correct them. Actually, there are only two categories. One is low fat, the other is regular. But because of the wrong entry of data, we have multiple levels. Combined here dot item fat content is equal to combined here dot item fat content dot replace. Replace is a function where first to give the pattern to be replaced. I am replacing small low, small fat, and I'm also replacing capital L, capital F with the replacement, which is low fat. The first one is pattern to be replaced with, pattern to be replaced. The second is what is the replacement? Here I am replacing small low fat and capital LF with L capital F capital low fat. Now, if I go up and do, you get the RG must be separate argument because we can't give everything in one go. It will take only one pattern at a time. Combined here dot item fat content is equal to combined here dot item fat content dot replace bracket REG is the to be replaced and it has to be replaced with regular. First, what is the pattern to be replaced? Then what is the replacement? Now we got the correction. See, low fat and regular, two levels. Pattern replacement function, string function, replace. Okay. Now let us check item visibility. The next variable combine here dot item visibility dot describe. So we have visibility, different metrics. There is no problem here. So visibility, there is no issues. So after visibility, item type, combined here dot item type dot value prompts. So we have different types of items here, fruits and vegetables, snacks. Different types of item types are there. Nothing problem here. So we have all categories of items here. Okay. See, what happens is this is small data set. Okay, so otherwise we can do like this. Numeric calls is equal to combined df dot select underscore b types include is equal to np dot number. Object calls is equal to combined df dot select underscore b types include is equal to square bracket single quote object. So we are splitting the data frame into numeric calls and object calls. So numeric calls dot columns. We have item weight, visibility, MRP, and establishment here. And object calls dot columns. We have all other variables. Now, item outlet sales is also coming as object because half of the data is object. So technically, we should move it to numeric calls. Numeric calls, square bracket single quote, item underscore outlet underscore sales is equal to object calls or item outlet sales. And then we have to immediately drop it from object calls. Yeah. Yeah, we have to immediately drop it, otherwise it will be duplication. Sales, comma, axis is equal to 1 because it's a numeric variable. Basically, sales is a numeric variable, but why it is coming in object is because half of the test data we have inserted the word test right there. So it is a mixed data type. Some data is numeric, the other data is object. So when it's a mixed data type, it will take it as object. So I am moving it from object to numeric. Now, once you have done that, you can take numeric calls dot describe. So it doesn't take outlet sales because it's a mixed type, but rest of it is giving. Visibility, weight, MRP, it is giving you the descriptive statistics. Now, if you look at the establishment here, it's the year of establishment. Now, what I can do is, based on that variable, I can create age of the outlet. Another numeric variable I can create called age of the outlet as of 2022. As of this year, what was the age of the outlet? And then we can delete the variable establishment year. Because years is nothing but 1992, 95, 98, like that, we get years. Instead of keeping it as years, we can extract the age of the outlet, which will be a numeric variable, which will give us more value addition compared to the years. So I'll create a new variable called outlet age, which is 2022 minus establishment year. So you'll get the age of the outlet as of the year 2020. That we can do. Okay, so numeric calls square bracket single quote outlet underscore age. This is the new variable I'm creating is equal to 2022 minus numeric calls dot outlet establishment year. Okay, so numeric calls dot describe. See, outlet age is a new variable which is added at the end. See, and the lowest outlet age is 13 years. The maximum outlet age is 37 years, with average outlet age of 24 years. Median is 23 years. Years. This is the age in years. Now we can delete establishment year because we have already calculated age. We can drop establishment year from our data because we no longer require it because we have already created a variable called age, which gives more information than simply establishment year. Simple establishment here will not be of any use until unless you extract some information from it. So here I am extracting the age of the outlet as of the year 2022. So now we can drop the establishment year. Which one? Which one? There is standard deviation, no? See, after calculating, you get the column of numbers. So, oh, okay, okay. You're getting confused. The actual data looks like this. See, 23, 13. This is the actual data. So the first outlet is 23 years old, second outlet is 13 years old, 23, 24 years old, 35 years old. These are the numbers. On that, we are calculating the mean and median and min and max. That's why you're getting those values. But otherwise, it's created a numerical column, which is the subtraction of 22, 22 minus the year value. So numeric calls is equal to numeric calls dot drop outlet establishment year, comma, axis is equal to 1, column dropping. Axis is equal to 1 is dropping the column, axis is equal to 0 is row dropping. Okay, so we have done the numeric calls. Now we have set of object columns, right? We have a set of object columns. We have a set of these object columns, right? Outlet sales, we have already dropped it. So object calls will not have outlet sales. Identifier also we have to drop, right? We have to drop this also, right? So object calls is equal to object calls dot drop item underscore identifier comma axis is equal to 1. Okay, now we have dropped the unnecessary column in object calls also. Now we can run a rule. For call in object calls dot columns column frequency is equal to object calls square bracket call dot value underscore counts print frequency. Now you will get the all variables in one go. This is the item fat content. This is for the item type, outlet identifier, outlet size, outlet location type, outlet type, and item code. You can print all the frequency counts in one go. Got it? So what we are trying to do is once you remove the variables which will not needed in both numeric and object calls, then you can do the describe of all the numeric calls. We'll get the complete description of the numeric calls, whatever we have. And then once you remove the unnecessary variables in the object calls, you run a for loop and print the frequencies. You get all the frequency counts in one go. So you can check your data. There is not much of a difference. The data is as of now okay. So select underscore data is very important. Whenever you have large data, we have to split it into numeric. We have to split it in object. Then one more thing, all numeric columns will not be numerical. Some of the numeric columns might be categorical, 0, 1 or like that might be there. So you have to separate them from numeric columns. The categorical columns, which might be there in numeric columns, must be separated, and a new Either you add them to object columns or create a new data frame called category columns. Okay, so you have to be very careful with numeric data. Some of the numeric data might be categorical in nature, particularly rating scales. 0 to 9 rating scale or 0 to 10 rating scale or 1 to 5 rating scales or what you call grades, gradings, right? Those sort of things you have to be very careful with the. There might be numerical categories. Like, take for example, 6-cylinder car, 5-cylinder car, and 4-cylinder cars. In car, you have cylinders, right? 3 cylinders, 4 and 5. Can we treat them as numbers? We can't, right? You have to treat them as categories. 3-cylinder car, 4-cylinder car, or 5-cylinder car. Similarly, gears. 5-gear car, 4-gear car, and 3-gear car. They are numbers only. Gear column will be there, 3, 4, 5 will be there. But can we treat them as numbers? We can't. You have to treat them as categories. So you have to be very careful when you're looking at numerical columns and identify such variables, which might be in numerical because of the data type, but they might be representing categories. And you have to separate them into separate categorical calls, or you have to add them into object calls, because they also have to be label encoded or dummy variable encoded. Okay. So we have studied all our variables. Now, let us look at object calls dot head. So this is our object calls. All text. All text. So what we have to do? We have to do dummy variable encoding. We have to do dummy variable encoding, wherein we convert the data into numbers. So the text data must be converted. So dummy variable encoding, like I told you, there are two methods: label encoding and get dummies. Now let us understand what they mean. Okay, so first I am doing label encoder. L capital label encoder. From sklearn dot preprocessing import label encoder. Okay. LE is equal to label encoder. I'm giving a short name to the label encoder. Object calls underscore label encode is equal to object calls dot apply LE dot fit underscore transform. Now object calls label encode dot head. Now you can see, right? All of them are assigned numerical identifiers. Now if I scroll up, low fat, regular fat. Now it is given, low fat is given 0, regular fat is given 1. Similarly, if you go to item type dairy, soft drinks, meat, dairy is given 4, soft drinks 14, meat is 10, alphabetical order. So you can see here, it's just assigning numerical identifiers to the levels, and the number of columns did not change. It has simply overwritten the columns with numeric identifiers. And the numeric identifiers are given based on alphabetical order. Here the data structure does not change. So if you look at our data structure, print object calls dot shape, print object calls label encode dot shape. See, 7 columns as it is. It has overwritten the text into numbers. And it will treat them as categories when they are passed through the algorithm. It will not treat them as numbers. Now, the second method, dummy variable encoding. Get underscore dummies. PD, pandas data frame. pandas get underscore dummies. Like I told you, na, binary encoding by adding more columns. So object calls underscore dummies is equal to pd dot get underscore dummies object calls. Now object calls underscore dummies dot head. Now you can see item fat content low fat, item fat content regular. It was earlier one column, right? Item fat content. It removed the original column. It replaced with two columns. And if it is low fat, 1 or else 0. If it is regular fat, 1 or 0. Similarly, it has created 42 columns, like, based on the different goods. See, baking goods, item type baking goods, item type breads, item type breakfast, canned, item type dairy, like that. It has created 42 new columns, outlet type, outlet supermarket, item code. We created 3 item codes, right? DR, FDN. So it has completely changed the shape of the data. Print object calls dot shape print object calls underscore dummies dot shape. See, 42 columns are now there. So get dummies will create new columns and add more columns to your data, and thus binary encoding. This is the preferred methodology used for both regression and classification, as long as we have enough data. Sometimes we might have less amount of data, then we will go with label encoding. And label encoding does not make much of a difference in classification problems, but label encoding plays a very important difference in regression problems. So whenever you are using regression problem or doing a regression method, always go for get dummies. Always use get dummies in regressions. Only exception is when you don't have enough rows. So take, for example, the minimum sample size required for regression is 20 observations per variable. Minimum sample size is 20 observations per variable for regression. For classification, minimum 50 observations per variable. So if your rule meets the condition, then you will expand the variables. If somehow you don't have enough data, then you will try to do it using label encoding. Here we have 48,520 trained data. Okay, 42 plus numeric calls are around 4, 45. You take it as 50 also. 50 into 20,000 only. But we have almost 8,000 rows. So we have enough data. Here we can use get dummies. Understood the difference between label encoding and get dummies? The transformation. Sorry, not transformation, dummy encoding, dummy variable encoding. Text must be encoded. Text must be encoded. You can't have text in your data. Okay, so this is the process we have to do on this. Now let us look at our numeric calls. Okay. Now these are the independent variables. We'll separate the item outlet sales, which is our dependent variable. We will separate our dependent variable. We have to look at the independent variables because data transformation on dependent variable is different, on independent variables is different. Okay, so we might look at the outlet sales at a later stage. As of now, what we will do is we will talk about data transformations. Data transformation, the scalars. Remember the scalars? Standard scalar, normal min-max scalar, or what we call robust scalar. Now, before we scale, it is always best to do a box plot. You remember box plot? Numeric calls dot drop item underscore outlet underscore sales dot plot kind is equal to box. No, what is big box? It says item outlet sales not found in accessor. Oh, sorry. I didn't give the this is equal to 1. Now these are the box plots we get of the different variables. In one single plot, we get the box plots of different variables. Item weight, item visibility. Visibility is a smaller number. You can plot it separately. Item MRP is a larger number. Outlet age is another, we can smaller box plot. Visibility might have outliers. You can see the black dots, right? So this is a method where we can do multiple box plots in one go. Okay, so we can see there are outliers in visibility. Rest of the data doesn't have any outliers. And if you look at the skewness also, we can't see them correctly. But we can try to plot the skewness. Numeric calls dot skew. Sorry, we have used the same drop function to calculate the skew. See, all of them are closer to 0, except visibility. That is the one which has outliers. You can see the black dots, right? You can see the black dots. That means there's a round black dots because it's getting covered up because of the other large variable sizes. So it is high skewness. Rest of all are closer to 0. We don't have any issues with that part, right? So for learning purposes, we will do the scalar. Okay. So first we will apply the standard scalar, which is based on Z score, which is x minus mean divided by standard deviation. This is the formula for Z score. This is the formula for Z score, which is used for transforming the variables. From sklearn dot preprocessing import standard scalar. Scalar is equal to standard scalar. Numeric calls underscore scaled is equal to copy the dot apply scalar dot fit underscore transform. Scalars. Okay, this should has to be done now. Scalar dot fit underscore transform. Now, PD dot data frame numeric call scale dot head. Now you see the data has changed. What is the actual data? The actual data is this. Oh, we didn't have the columns, right? So we can do columns. Columns is equal to numeric calls might give an error. Yeah, because that item outlet sales is there, no? You have to manually give. Okay. So we got the headers also. Because scaling will convert the data into NumPy arrays. That is why I'm converting back to data frame. Because scaling will convert the data into NumPy array. Arrays, it will convert into arrays. So we are converting it back to data frame. Data frame, we are converting the arrays to data frame, and we have to give the column headers. Generally, we give the x dot column sequence because item outlet says we have not there, no? So we have to manually give the list. Otherwise, we can just give the previous data frame dot columns, it will add the columns. So this is the process of standard scaler where you got negatives and positives, right? So this is standard scaler which we have done on the numerical data. Now, normalization or min-max scalar, right? From sklearn dot preprocessing import min-max scalar. Normalize is equal to min-max scalar. Numeric calls underscore normalize is equal to copy from top. So we'll change the scalar to normalized. Rest of it all same. Okay. Now pv dot data frame numeric calls normalize comma. We'll copy the columns from top. Top. See, all the values are between 0 and 1. There are no negative values. There are no negative values. All the values are in positive order. Scaling, min-max scaling. This is your standard scaling. Standard scaler, min-max scaler, and the last one is the robust scaler. From sklearn dot preprocessing import robust scalar. Robust is equal to robust scalar. Brackets. Now, numeric calls underscore robust is equal to copy the command from top. Simply change the robust dot shape. Again. Pv dot data frame numeric calls underscore robust comma. We'll get the columns command from top. dot health. So we got the robust scalar. So robust scalar will give you negatives also. Okay. So these are the three transformations which we can do on dependent variable. The three transformations which we can do on dependent variable are standard scalar, min-max scalar, and robust scalar, depending on the data we are dealing with. Whatever data you are dealing with, based on that, you have to do the scaling accordingly. Okay. So, but before scaling, you have to plot the box plots. Okay, so that you can see which variables have the outliers. Right. Now, if you do the box plot, dot plot time is equal to box. See, now the plots are visible, and but still outliers are existing on visibility. Now you can see that the scaled data looks similar to one another. Earlier they were completely to one side, right? But still we have outliers in visibility. The boxes are also a little bit okay. Not that great, but okay. This is somewhat cleaning our data. From a completely skewed or this data, you're getting some structure back to the data, which will help you to analyze properly. Similarly, after the scaled columns, you can also check, this is what normalize, right? Yeah. See, normalization is giving us even more prominent things, right? Normalization is giving us even more thing. The data range looks very normalized. 0 to 1 only, na? All value you can see on the y-axis. It is purely 0 to 1. Okay, so this also gives us, and the last one, robust. The robust should do something on the outliers, but it is not able to do anything on the outliers. So it is keeping the outliers as it is, but the boxes also to some extent has improved, but not that great. See, you can't eliminate outliers. Remember that part. We can't eliminate skewness. We can't eliminate kurtosis. We can only minimize them to an acceptable level. We can only minimize them to an acceptable level. We can't make them zero. It's zero is only hypothetical. In real-time data, you will have lots of skewness, lot of columns will be there. We have to clean up, we have to do a lot of activities, and then only we get a structure of data for analysis. So here also, we are looking at the transformations, how the data is transformed by different scalars, how each scalar is affecting the data that we are trying to understand. Using the best plots would be box plots, comparative plots, which is easy to run and easy to interpret also. Okay, so you can give vertex equal to false, and then you can do the skewness also. So this is what we can do with data transformation. Now, once we have the data properly done, then we can combine the data into one single data frame. So let us say combine df underscore clean is equal to pd.uncat square bracket numeric calls comma object calls dummies comma axis is equal to 1 because numeric calls next to it object calls done, right? Now, what we will do is, we have cleaned our data frame, we have certain extent. Now we can do the splitting. We can split the data back to train and test. Bigma train underscore df is equal to combine df underscore clean square bracket combine df underscore clean dot item outlet sales not equal to test. All the cells that are not equal to test will be selected as train data. Bigma test underscore df is equal to combine df underscore clean square bracket combine df underscore clean dot item outlet sales double equals to test. All the cells that are with the word test will be selected as test data. Right? Now, Bigma train test df is equal to Bigma test df dot drop the item underscore outlet underscore sales, comma axis is equal to 1 is column dropping. We have added that column, right? Now we are dropping our column. Now we will split train data into y and x. Y is your dependent variable, x is your independent variables. Y is equal to Bigma train df dot item outlet sales. Capital X is equal to Bigma train underscore df dot drop. We have to drop the dependent variable, right? Item underscore outlet underscore sales, comma axis is equal to 1. Now we have to run the plots on dependent variable. We have to run the plots on dependent variable. What plots? Hist, box, and density. Because the fundamental assumption is they must be closer to normal distribution. So y dot plot kind is equal to hist. See, positive skewness. We have positive skewness. All the bars are onto the left side. Similarly, y dot plot kind is equal to box, comma, what is equal to box. See, there are outlets. And the box is onto the left side. Positive skewness. Y dot plot kind is equal to density. You can see here positive kurtosis, positive skewness, and long tail. So now we have our data. Now what we should do when you have positive skewness, we have to do what transformation? In the top, I told you, dependent variable. When the dependent variable has positive skewness, what we should do? Logarithmic transformation. Right. So let us try logarithmic transformation. NP dot log sigma train df, sorry, NP log y dot plot kind is equal to box, comma, what is equal to false. What happened? Float object has no attribute log. Okay. What? Conda series only. Y dot head. Yeah, we have all the values. So np dot log of y dot float object has no attribute log. New problems will come here. Acha, we have to convert the data type. Because it was earlier both mixed type, na? So we have to convert the data type. Y is equal to y dot as type. Float 64. How it is working. Dot plot child is equal to box, comma, but is equal to. See, it moved the outliers to this side, from that side to this side. So it is not a good one. And the second thing is, in sales, you will have outliers. In sales, you'll have outliers. Some people will do exceptionally good performance. Some people will do exceptionally bad performance. So we can't do anything about that. We have to use with outliers models like decision tree or something like that. Base model might not work, multiple linear regression. But we have to use such model. So let us try the other one also, np.sqrt. So SQRT is bringing to some extent the box to the middle, square root. But not much of a difference. It is not doing much change. So we will keep y as it is without any transformation, and we will use models that work well with the outliers and skewness. So this is the whole process of data preprocessing, which we have done, which takes lots of time. In real life, we will be spending days on doing a lot of transformations on data because the data will be large. And then accordingly, we will be working on the pre-processings. So just go through this notebook whenever you have time. Okay, this will help you a lot. And whenever we do any competition data, we have to do pre-processing. That HR analytics data also is there. We have to do pre-processing on that data also, HR analytics. We have one competition, Kegel house price, where we have 80 variables, out of which half of the variables have missing values. So we have to deal with that sort of things also. So we will be working on data where we have a lot of pre-processing to be done. So I will also introduce you to the what we call imputers as we go through the process. So please be careful with the missing values and transformations. Interview questions will come there also. When to use what transformation and all those things. Okay, you can expect a lot of questions there. Okay. So, any doubts? You can ask, or we can end the session for today, and we'll meet in the next session. Okay. So I have emailed the books. I will upload the video once it gets converted. All of you got the Gmail folder access, right? All the videos are there. So this video also I'll upload as soon as the conversion stop. Sitaram, any doubts?
No, sir.
Yeah. So any doubt we will discuss next class also, because this is a constant process. Any real-time data we have to go through pre-processing. Pre-processing
Yes.
will create new challenges.
Okay, okay. Sir.
So I'm stopping the share, okay?
Okay, sir.
Thank you. Thank you. Thank you for participating. Thank you.
Thank you, sir.